Hi all, this is Anthony Saul again, and then now we are going to the last part of the uh, Z operating system. Now we're going to discuss the important component. Uh, we first going to discuss the RAM that uses in the ZOS. No? ZOS uses what we call the uh, uh, NOMA or non-uniform memory access. This is a computer memory design used in primarily in multiprocessing. So because ZOS is a multiprocessing, so that's why it uses another standard for memory, where the memory access time depend on the memory location related to the processor. No? As I said in the earlier slide, the compartment between CPU and memory are close together. No? So this is the reason why they are close together, because they uses what we call the non-uniform memory access. No, uh, to understand this, let's take a look the uh, uniform memory access that typically used by server or in our uh, typical computer. No, as can you see here, we have processor, and then the processor is going to communicate to the memory controller before they going to access the memory. Uh, because of that, they have some delay in processing the data. Unlike in the Z system that uses using the ZOS, the CPU has direct access to the RAM. So to better understand this, I simplify it into more details, something like this. In and uniform memory access memory standard, you have memory controller that is responsible for accessing the memory and connected to the processor. Unlike in NUMA or non-uniform memory access, this is a kind of memory architecture that allow a processor uh, faster access to the memory, because it has no memory controller, no, rather than dun sa traditional nga na may memory controller pa, no. In other word, in NUMA architecture, a processor can access local memory much faster. This is because the NUMA setup, uh, each processor is assigned a specific local memory exclusively for its own. So this eliminates sharing of non-local memory, reducing delay with multiple requests come in access for memory location. So sa non-NUMA setup kasi, there will be a buffer between or bottleneck dun sa memory controller, because all the traffic will be going to this memory controller before accessing the memory. Unlike in a NUMA setup, all the processor has a direct access to the memory. So that is why uh, in the mainframe setup that I showed you earlier, the slot for the processor and memory are they are enclosed into one slot. In this slide, you can see here that the uh, processor has direct access to the RAM or redundant array of independence memory. We're going to discuss this in this slide, but this part set of RAM already has direct connection to the control unit, and this specific control unit has a termination point for the another component like this one, the storage. Uh, these are the redundant array of independent memories or the RAM. RAM utilize the additional memory module and stripping algorithm to protect against the failure of particular module and keep the memory system operating continuously. Uh, the RAM setup is similar to the concept of a RAID setup or redundant array of independent disk, but uh, in this particular setup, it is protect protects against failure in memory. If one of these slot here are failed, they can easily take out one of the uh, slot here without uh, need to interrupt the process, because in mainframe computer we say that it is uh, no zero downtime, no. So if one of here is failure, so the process still continue, and then the data here will be reallocated to the another uh, slot here. And RAM also has some sort of parity checking and error correction code memory or ECC memory. This particular technique also see in a ordinary memory controller. And then now we go into the CPU of the ZOS. The ZOS uses the dual core Z9 CPU chip. As can you see here in the slide, it is a uh, CPU that is not uh, uh, soldered in a traditional uh, printed board circuit, no, but instead it is in the ceramic substrate. As can you see here, it is composed of 16 chips. These chips is measured approximately between 15.66 millimeter by 15.40 millimeter, and it's carry a 660 million transistor. Among the 16 chips that you can see here are 8 for the processing unit, 2 for miscellaneous or memory subsystem control function, and 4 for system data cache, and 1 for storage controller, and of course 1 for the system clock. The advantage of using ceramic compared to the printed circuit board, siyempre for the uh, more uh, faster interconnection, because here you can have many set of chip into one frame, and also improve uh, the speed by controlling the temperature, because one of the primary reason of the CPU performance is the overheating. So much improved cooling system here in the ceramic substrate uh, compared to the printed circuit board. Uh, Here we can see if you're going to pull out the one of the component here, for example the processing unit, you can see here it is has 2 core, and the storage controller here will be the responsible for transferring of frame and pages between real storage, auxiliary storage, and virtual storage. And then oh, we have the SD here for the data cache of the process information, and the memory subsystem control function. Here will be the controller of the uh, another subsystem. For example, this is where the memory are uh, directly connected to the NMC. And also important is the system clock to synchronize the speed of CPU to the memory.